Welcome to the deep dive. You know how sometimes you want to understand something complex without slogging through hundreds of pages?
Definitely.
That's what we're doing today. We're taking a fascinating journey into the world of computer vision, and our roadmap is the book Learning OpenCV for Computer Vision with Python 3 by Joseph Howse and Joe Minichino. Think of this as your shortcut to grasping how computers can, well, see and interpret images, from basic tweaks to some seriously smart AI.
Exactly. This book is packed with techniques that power everything from, your smartphone's camera to advanced robotics.
Yeah.
What's great is the sheer variety. It covers how to handle images and videos, detect objects, even understand depth. Our mission today is to pull out the most crucial insights so you can understand the core principles without getting lost in all the technical weeds.
Yeah, cut through the noise. So if you've ever wondered how your phone recognizes faces or how self-driving cars see the road, you're in the right place. Let's dive right in, starting with the very first step, getting OpenCV up and running on your computer.
Right. The book guides you through setting up OpenCV on Windows, macOS, and Linux. Now, this can sometimes feel like a hurdle, but the key takeaway is ensuring your system can find the necessary OpenCV libraries. On Windows, for example, you might need to tweak your system's path variable.
Ah, the infamous path variable.
Yeah, think of it like telling your computer where to look for specific tools. It's crucial.
Right, it's like making sure all the ingredients for a recipe are in the right place so you can actually cook. And for those using Python, the book points out that the actual OpenCV module, the cd2.pylori file, usually lives in your Python installation's site packages folder. Knowing that can be helpful for troubleshooting if things don't work right away. Now, once OpenCV is installed, you're going to want to start actually working with images and videos.
Absolutely. The foundation of computer vision is interacting with image and video data. And OpenCV provides the tools to seamlessly move between what's on your hard drive, what your camera sees, and how the computer holds that information in its memory. The book explains how images are often represented numerically. In grayscale, each pixel has a value from 0, which is black, to 255, which is white. In BGR, that's blue, green, red, kind of backwards from the usual RGB.
Right, that always trips people up initially.
It does. But yeah, each color channel also has a value in that 0 to 255 range.
So it's all just numbers at the end of the day. And the book shows how you can convert these image numbers into something Python can easily work with. NumPy arrays.
Yes, NumPy is essential here.
But a reshape function is like a translator, right?
Yeah.
Allowing you to take a string of these pixel values and organize them into a grid that represents the image.
Exactly. And this is where things get powerful. NumPy arrays are the lingua franca of image manipulation in Python with OpenCV, allowing for fast, vectorized operations on pixel data.
Vectorized meaning doing calculations on whole chunks of data at once.
Precisely. Much faster than looping through pixel by pixel. The book demonstrates how you can directly access and even change individual pixel values using array indexing. For even more precise control, you can use the item method to grab a specific color value at a specific pixel location and item set to change it.
Okay, so you could like pinpoint one red pixel and make it blue.
You absolutely could. Imagine you want to slightly tweak the redness of a single spot in an image that's the level of control you have.
Neat. Beyond static images, the book covers how to handle video.
Yeah, and at its core, a video is just a series of still images played in rapid succession, right? Frames.
Right.
OpenCV lets you read and write these video files. And for capturing live video, the cv2.videocapture0 command is your gateway to your computer's camera. That 0 usually signifies the default camera. If you have multiple, you might use 1, 2, and so on.
Got it.
What's fascinating here is how the book immediately gets you thinking about how you, the user, can interact with these images and videos through graphical interfaces. It explains how cv2.mshow creates windows to display images and those live camera feeds. Think of it as your canvas for seeing what the computer sees.
But simply displaying isn't enough, right? You need to be able to react to what's happening or tell the program what to do next.
Exactly. The book covers handling keyboard input with the cv2.waitKey function. This is crucial. It pauses your program for a bit, waiting for you to press a key.
Okay, so it doesn't just freeze.
No, it waits for a specified time in milliseconds.
Yeah.
If you press a key during that time, it returns the ASCII code of that key. If not, it returns NAS1. The book even mentions the ORD function in Python, which lets you find out the ASCII value of any character so you can check, like, if the user pressed Q to quit.
Ah, useful.
And cv2.waitKey isn't just passively waiting. It's the crucial link that allows those OpenCV windows to update and draw themselves properly. It's kind of the heartbeat of simple OpenCV GUI apps.
Right, keeps things responsive.
And the book also dives into mouse events using cd2.set mouse callback. This lets you define a function that gets called whenever you do something with your mouse in an OpenCV window. A click, a move, releasing a button, providing you with information about the event type and the mouse's X and Y coordinates.
So you could say, click on a pixel and get its color value?
Absolutely. Or draw a box or select a region. Lots of possibilities.
Now, all these fundamental ways of getting data in and out and interacting with it set the stage for something really neat the book introduces, Project Cameo. What's the big idea behind that?
Cameo is a clever example of how to organize your code for more complex video processing tasks. The core idea is to create reusable components classes, really that handle the nitty-gritty of getting video from different sources and managing the display windows and keyboard inputs.
Okay, like separating concerns.
Exactly. The book introduces managers.captureManager to handle video input, whether it's from a file or a camera, abstracting away the details. And managers. Window Manager takes care of the window creation, destruction, and keyboard event handling in a more structured way.
So instead of writing the same setup code over and over again every time you want to grab video or handle a key press, these manager classes take care of it for you.
Precisely. And then the Cameo. Cameo class ties everything together. It uses these managers and has a central run method, which contains the main loop. Grab a frame, process it, show it, handle input. It provides a basic framework for building your video application. It's all about keeping your main image processing logic separate and clean.
That makes a lot of sense for bigger projects, keeps things maintainable.
It really does. This separation makes your code much easier to understand and build upon. Now, once you have those images or video frames flowing in, the next step is to start manipulating them, and that's where image filtering comes in.
Okay, let's talk about how to actually change the pixels themselves. The book starts with image filtering using convolution with custom kernels. That sounds a bit mathy.
It is, conceptually, but OpenCV makes it practical. It mentions that while NumPy has a basic convol function, for the multidimensional data of images, you'll often turn to SciPy's endimage.convolve, or more commonly within OpenCV itself, cv2.filter2d for general 2D filtering. There's also cv2.setFilter2d for certain filters that can be broken down for better performance.
Okay, but what's a kernel in this context?
What's fascinating here is the concept of a kernel. Think of it like a small grid of numbers, maybe 3 by 3 or 5 by 5 pixels, a little stamp or stencil that you slide across your image, pixel by pixel.
Okay.
At each position, the kernel's numbers are multiplied with the underlying image pixel values, and the results are summed up to produce the new value for the center pixel in the output image. The pattern of numbers within this kernel determines how each pixel in the original image is modified.
Ah, so the kernel defines the effect of the filter.
Exactly. The book gives great examples, like using cv2.Gaussian blur to smooth out noise, making the image a bit blurry. This uses a kernel based on a Gaussian function. And then there's high-pass filtering, which does the opposite. It emphasizes differences between adjacent pixels, which can sharpen details and enhance edges.
And speaking of edges, the book then delves into edge detection specifically.
Right. It introduces common predefined filters like Laplacian, Sobel, and Char. These have kernels specifically designed to highlight areas where the intensity of the pixels changes rapidly, which is typically where you find the edges of objects.
But these can pick up noise too, can't they? Like random specks might look like edges.
They absolutely can. That's why the book often recommends blurring an image first, using something like Gaussian blur to reduce noise before applying an edge detection filter. That usually gives you a cleaner edge map.
Makes sense. Smooth it out, then find the edges.
And for blurring, OpenCV gives you a few options. The simple blur function, which just averages the pixel values in a neighborhood. Median blur, which takes the median value instead of the average, and is particularly good at removing those random black and white salt and pepper noise pixels. And the Gaussian blur we mentioned, which uses a weighted average.
And they all have this mate size parameter.
Yes, a key parameter for all of these is 8 size, which defines the size of that neighborhood or kernel, like 3 by 3, 5 by 5, etc. It's always given as an odd number representing the width and height in pixels. A larger size means more blurring or a filter that considers a wider area.
The book even shows you what these kernels actually look like, the specific arrangement of numbers in the matrix for a basic edge-finding filter and a blur filter.
Yeah, seeing the numbers helps visualize how they work. For example, an edge filter might have positive numbers on one side and negative on the other to detect changes.
They also touch on creating embossed effects, like making the image look stamped.
Right, which you can achieve with asymmetric kernels, ones that have positive values on one side and negative values on the other, often offset diagonally. It creates that illusion of depth or relief by emphasizing edges in a particular direction.
Cool. Okay, so beyond just tweaking pixel brightness or finding edges, OpenCV provides powerful tools for understanding the shapes within an image, right? Through geometric transformations and analysis.
Exactly. The book covers finding contours using CV2.findContours. Think of contours as the outlines of objects or connected regions that have the same color or intensity. It's a really fundamental tool.
And there are different ways to find them, like retree and retrexternal.
Yes, it's important to note the different retrieval modes. CV2.retrieve, for instance, gives you the full hierarchy of contours like detecting a hole inside a shape, which would be a separate contour nested within the outer one, whereas CD2.retrexternal just gives you the outermost boundaries, ignoring any holes.
And the approximation method, chain approximable.
Right, that controls how the contour points are stored. CV2.chain-to-proc-simple is really efficient. It simplifies those outlines by only storing the endpoints of straight-line segments. So for a rectangle, it would only store the 4 corner points, not every single point along the edges.
Saves memory, I guess.
Definitely. Once you've found these outlines, you'll likely want to do something with them. The CV2.drawContours function lets you draw these lines back onto an image, maybe in a bright color, so you can see what was detected.
Okay.
The book also mentions other useful operations you can perform on contours. CV2.arcLength calculates the perimeter. CV2.approxPolyDP tries to fit a simpler polygon shape with fewer vertices to a more complex contour within a certain tolerance. And CV2.convexHull finds the smallest convex shape, like stretching a rubber band around the contour points that encloses it.
What would you use convex hull for?
Oh, things like checking for defects in objects, or simplifying shape representation, or even as a step in gesture recognition sometimes. These are all incredibly useful tools for analyzing the shapes of detected objects.
Absolutely. Now, let's shift our focus a bit. The book then moves into the fascinating area of understanding the three-dimensional world from two-dimensional images through depth estimation and segmentation, essentially, figuring out how far away things are and separating different objects in a scene.
Right, this is where things get really interesting, moving beyond flat images.
This part starts by introducing depth cameras. These aren't your standard webcam. They capture more than just color, right?
Exactly. They use various technologies like structured light or time of flight to measure distance. They can provide different maps. A depth map is common, where each pixel's value, instead of color, tells you its distance from the camera, often in millimeters. Then there's a point cloud map, which actually gives you the 3D coordinates, x, y, z, for each pixel in the camera's view. And sometimes you get a disparity map, which relates to how much an object's apparent position shifts when viewed from a slightly different angle, similar to how our two eyes perceive depth. The book lists constants, like CV2.capopenna depth map, CV2.capopenna point cloud map, CV2.capopenna disparity map that you might encounter when using APIs like OpenNI to access these cameras.
So lots of different kinds of data coming from one sensor.
Pretty much. And it's really important to understand what kind of data these maps provide. Like I said, a depth map often stores the distance in millimeters, maybe as a 16-bit unsigned integer, which gives you a much wider range of values than a standard 8-bit image.
Right, 0 to 65535 instead of 0 to 225.
Exactly. The book also mentions CV2.capopennavalid depth mask, which is a helpful map indicating which pixels have reliable depth measurements and which ones might be invalid, maybe too close, too far, or on a difficult surface. And of course, these depth cameras often also capture regular color, BGR, grayscale, and even infrared images, so you can correlate the depth with the visual appearance. Constants like CV2.capopenimage reflect that.
Now, because depth data often has more detail, like that 16-bit range, compared to standard 8-bit images we display on screens, the book talks about converting it, right? Why is that necessary?
Yeah, it's mainly for display purposes. Your monitor typically displays 8 bits per color channel. So if you just try to show a 16-bit depth map directly using CV2.mshow, it might look completely black or white because the range is so much larger.
So you have to scale it down.
You usually have to scale or normalize the 16-bit values into the 0255 range to visualize them effectively. The book explains that while CV2.mshow tries to do some automatic scaling for certain data types, it might not always guess the right range for depth data, leading to poor visualization. So you often need to handle the conversion explicitly.
Got it. Okay, what about using that depth info for segmentation, separating foreground from background?
One clever technique the book covers for basic segmentation is creating a mask from a disparity or depth map. It introduces a create median mask function as an example. This uses NumPy's median function to find the most common depth value in the central part of the image, assuming that's likely the background or main surface.
Okay.
It then creates a binary mask, black and white, that highlights regions with depth significantly different from this median value, effectively separating a foreground layer, assuming it's closer or farther than the median.
Simple, but potentially effective for some scenes. What about more interactive ways?
For more interactive segmentation, where you can guide the process, the book outlines the grab-cut algorithm, cv2.grabcut. This is a really powerful tool. You typically draw a rough bounding box around the object you want to isolate.
Just a rectangle.
Yeah, or you can provide more detailed hints with a mask marking definite foreground and background pixels. The algorithm then iteratively refines that initial segmentation using color and texture information to figure out the precise boundary between the object and the background. It's quite neat.
And watershed. That sounds watery.
Yeah, the watershed algorithm is another segmentation method mentioned briefly. The metaphor is thinking of the image intensity landscape as a topography. You flood it from different starting points, markers, and the boundaries where the floods meet form the segmentation lines. It's often used when you want to segment an image into multiple distinct regions, especially if they're touching or overlapping.
Interesting. Okay, moving from understanding the depth and structure of a scene, the book then tackles the really engaging topic of detecting and recognizing faces. This is something we see everywhere now.
Absolutely. It's a classic computer vision task. The book starts by explaining how hair cascades can be used for face detection. These are based on work by Viola and Jones from the early 2000s, a real breakthrough at the time.
Pair features. What are those exactly?
Well, there's simple rectangular features, some black, some white. You slide them over the image, and the difference between the sums of pixel intensities in the black and white regions is calculated. Certain patterns of these features, when combined in a cascade structure, are very effective at quickly identifying face-like regions while discarding non-face regions.
So it's like a multi-stage filter.
Exactly. Early stages quickly reject obvious non-faces, and later stages do more detailed checks. It's fast. However, the book is careful to point out their limitations. They're primarily trained for frontal faces and can struggle if a face is tilted significantly, partially occluded, or viewed from the side. Lighting conditions can also affect them.
Still pretty useful as a starting point. How do you use them in OpenCV?
The good news is that using them in OpenCV is quite straightforward. You use cv2.cascade classifier to load the pre-trained cascade data. These usually come as XML files. You've probably seen names like arcascade frontal face default.xml.
Yeah, I've seen those.
Then you just call the detect multiscale method on your image. Usually grayscale works best. This method scans the image at different scales, hence the name, and returns a list of rectangles where it thinks it found faces.
And you can tweak it.
Yeah, it's interesting that this function has parameters like scale factor, how much the image size is reduced at each image scale, min neighbors, how many neighbors each candidate rectangle should have to retain it helps filter false positives, and min size, minimum possible object size. Tuning these can affect performance and accuracy.
The book even shows how you can use multiple cascade classifiers together.
Right, you can load one for faces and another one for eyes, for example. After detecting a face, you can then run the eye detector just within the face region to find the eyes.
Okay, so that's finding a face. What about knowing whose face it is? Face recognition.
Right, building on simply finding a face, the book introduces the fascinating area of face recognition, actually identifying who that person is. It highlights three main algorithms implemented in OpenCV4: eigenfaces, Fisher faces, and local binary pattern histograms, or LBPH.
Eigenfaces and Fisher faces. They sound related.
They are. Both use a technique called principal component analysis, PCA, or a related method called linear discriminant analysis, LDA, for Fisher faces. The core idea is to find a set of principal components, or eigenfaces basically, abstract facial features that best represent the variations across a data set of training faces. A new face is then represented as a combination of these eigenfaces.
And LBPH is different.
Yeah, LBPH takes a different approach. It doesn't look at the face globally like eigencases, Fisher faces. Instead, it looks at the local texture patterns around each pixel. It compares a pixel to its neighbors and creates a binary number representing whether the neighbors are brighter or darker. Histograms of these binary patterns across different regions of a face form the descriptor. It's often considered more robust to variations in lighting.
Okay, 3 different approaches, but the process is similar.
The common thread with all these algorithms is that you first need to train a model. You feed it a collection of labeled face images, multiple pictures of each person you want it to recognize, ideally under various conditions. The algorithm learns the distinguishing features for each person.
And then you test it.
Then, when you give it a new unseen face, after detecting it first usually, you use the trained model's predict method. It tries to match the new face to one of the people it was trained on, and typically returns the predicted label, the person's ID, and often a confidence score or distance measure. A lower distance usually means a better match. The book shows a basic example of how to do this in a video feed.
That's really cool. The book even touches on a fun application, face swapping.
Yeah, just briefly. In the context of the Project Cameo example, it mentions a helper function, copyrect, and the clever use of numpy.where. If you detect two faces, you can basically copy the pixels from the rectangle of one face onto the location of the other face. But numpy, where lets you do it selectively, maybe using a mask, so you're only copying the face pixels and not the background within the rectangle. Creates that fun, sometimes creepy swapped appearance.
Yeah. Okay, so we can find and even recognize faces. But what if you want to find other specific things in images, like landmarks and photos, or maybe find duplicate images? The book then transitions to how to retrieve and search for images based on their visual content using image descriptors.
Right, this is moving towards content-based image retrieval, CBIR, and feature matching. How do we describe the content of an image in a compact, searchable way?
Image descriptors are the key here.
Exactly. Image descriptors are like fingerprints for images, or image regions, numerical representations of distinctive features that can be used to compare images and find similar ones, even if they're transformed in some way.
So how do we get these descriptors? The book mentions Harris corners first.
Yeah, Harris corner detection, CV2.corner Harris, is one of the earlier methods. It looks for points where the intensity changes significantly in multiple directions, basically, corners. It gives you a score for each pixel, indicating how corner-like it is. You can then threshold this score to find the actual corner points.
But you mentioned earlier they weren't great if the image is scaled.
Right, that's a key limitation the book points out. If you zoom in or out, the appearance of a corner changes, and the Harris detector might not find it reliably. That's why the book introduces more robust methods like scale invariant feature transform, or SIFT, developed by David Lowe.
SIFT sounds important.
It was huge. SIFT is designed to find key points in an image that are distinctive and remain detectable, even if the image is scaled, rotated, or partially affected by changes in illumination or 3D viewpoint. It generates a high-dimensional descriptor vector for each key point.
And SRF.
Speeded up robust features, or SRF, came a bit later. It aims to provide similar robustness to SIFT, but much faster, using approximations based on integral images. Both SIFT and SURF were patented, though, which limited their use in some contexts, although the patents have started expiring.
Ah, patents. So what's the free alternative? Or RB?
Exactly. Or ORB, which stands for Oriented Fast and Rotated Brief, was developed partly as an efficient and free alternative. It combines a fast key point detector, FAST, with a rotation-aware binary descriptor, BRIEF. Binary descriptors are very compact and fast to compare, making ORB for real-time applications like visual SLAM, simultaneous localization and mapping, where speed is crucial.
So for all of these SIFT, S, or RB, the process is find key points and compute descriptors.
Generally, yes.
Yeah.
Find interesting, stable points in the image, the key points, and then create a numerical description, the descriptor, for the local image patch around each key point.
Okay, now you have descriptors for two images. How do you match them?
Once you have these descriptors, you need a way to see how similar they are between two images. The book covers brute force matching using CV2.bf matcher. This is exactly what it sounds like. It compares every single descriptor in the first image, the query set, to every single descriptor in the second image, the train set.
Finds the best match for each one.
Finds the closest match based on some distance metric. You tell it what kind of comparison to do, like using CV2.normal1 or CV2.normal2 Euclidean distance for SIFT-SURF descriptors, or CV2.norm hamming for binary descriptors like ORBRIEF, which just counts the number of differing bits.
And cross-check.
The cross-check option adds a consistency check. It requires that the best match from image A to image B must also consider the point in A as its best match when searching from B back to A. It helps eliminate ambiguous matches.
Okay, but brute force sounds slow if you have thousands of features.
For really large sets of descriptors, that brute force approach can definitely take a while. That's where FLAN-based matching using CV2.FLAN-based matcher comes in. FLAN stands for Fast Library for Approximate Nearest Neighbors.
Approximate. So it might not find the absolute best match.
It might not, but it's usually very close and significantly faster, especially for high-dimensional descriptors like SIFT. It uses clever data structures like KD trees or LSH, locality-sensitive hashing, to quickly find likely neighbors without comparing against everything. It's a trade-off between speed and guaranteed optimality.
Makes sense. Now, even with these methods, not every match found is going to be a good one, right? There might be false matches.
Absolutely, especially if the images contain repetitive patterns or aren't that similar. The book discusses ways to filter out the bad matches. One very common and effective technique is Lowe's ratio test, often used with k-nearest neighbors, KNN, matching.
How does that work?
Instead of just finding the single best match for a descriptor, you find the two best matches using GNMatch with K2. Let's say the distance to the best match is D1 and the distance to the second best match is D2. The ratio test says you should only keep the match if D1 is significantly smaller than D2 specifically, if D1 ratio D2, where the ratio is typically around 0.7 or 0.75.
So if the best match isn't much better than the second best match, you discard it.
Exactly. The idea is that a truly distinctive feature should have one clear best match, much better than any others. If the top two matches are very similar in distance, the match is considered ambiguous and likely incorrect. It's a very effective filter.
Okay. The book also briefly touches on finding the homography. What's that about?
Right. Once you have a set of good matches between two images of the same planar surface viewed from different perspectives, you can find the homography matrix. This is a 3x3 matrix that mathematically describes the perspective transformation, rotation, translation, scaling, sharing, that maps the points from one image to the corresponding points in the other image.
What's it used for?
Lots of things. Image stitching to create panoramas, aligning images, augmented reality overlays on planar surfaces, measuring distances on a known plane. OpenCV has functions like CD2.find homography that calculate this matrix from the matched key points, often using ransack to be robust against any remaining bad matches.
And finally, this leads to image search.
Yeah, the chapter outlines how you could build a basic image search system. You'd pre-process a database of images, extract descriptors, like SIFT or O or B, from each one, and save them. Then when you have a query image, you extract its descriptors and use FLAN to quickly find the best matches against all the descriptors in your database. By applying the ratio test and counting the number of good matches for each database image, you can rank them by similarity to the query image. Setting a threshold on the number of good matches helps decide if an image is relevant or not.
Very cool. Okay, we've talked about finding general features and matching images. Now, how do you train a computer to specifically find things like cars or people in an image? That's what Chapter 7 is all about, building custom object detectors.
Right, moving from generic features to specific object classes. This chapter introduces another powerful way to describe image content, especially for object detection. Histograms of oriented gradients, or HOG.
HOG, how does that work?
HOG works by dividing the image into small square regions called cells. Within each cell, it calculates the gradient, magnitude, and direction of intensity change for every pixel. It then creates a histogram summarizing the distribution of gradient directions within that cell.
So, a summary of edge directions in a small patch.
Pretty much. Then, these cell histograms are grouped into larger, possibly overlapping blocks, and the histograms within each block are normalized. This normalization step makes the descriptor less sensitive to overall changes in lighting and contrast. The final HOG descriptor for the detection window is formed by concatenating all these normalized block histograms.
And this is good for detecting people.
HOG features turned out to be particularly effective for detecting pedestrians and other objects with somewhat defined shapes and contours.
Now, when you run a detector, you often get multiple boxes around the same object, right?
Yes, a common problem in object detection, especially when using techniques like sliding windows, is that you might end up with multiple overlapping bounding boxes, all trying to identify the same object, perhaps at slightly different scales or positions. The book explains non-maximum suppression, or NMS, as the standard solution.
How does NMS work?
NMS is a post-processing step. It takes all the detected bounding boxes for a particular object class, along with their confidence scores, how sure the detector is. It sorts them by score, selects the box with the highest score, and then removes any other boxes that significantly overlap with it. For example, overlap more than 50%. It repeats this process until all boxes have been either selected or suppressed. It ensures you only get one or fewer detection per object.
Makes sense. Now, to actually decide if a window contains the object, based on its HOG features or whatever, you need a classifier. The book mentions SVMs.
Right. To actually decide whether a set of HOG features, or any other type of features extracted from an image window, represents the object you're looking for, you typically need a binary classifier. The book provides a high-level overview of support vector machines, or SVMs.
What's the core idea of an SVM?
Think of an SVM as trying to find the best boundary, a line in 2D, a plane in 3D, or a hyperplane in higher dimensions that separates your data points into different categories. For object detection, it's usually object versus non-object background. The best boundary is the one that has the maximum margin or distance to the nearest data points of either class. These nearest points are called the support vectors. This maximum margin property often leads to good generalization on unseen data.
Okay, so you train the SVM with examples of object features and non-object features.
Exactly. You give it lots of labeled examples, and the SVM learns the optimal separating hyperplane. Then, when you extract features from a new image window, you feed them to the trained SVM, and it tells you which side of the hyperplane they fall on object or not.
The book then shows you how to use a pre-trained HOG detector for people.
Yeah. Conveniently, OpenCV comes with a HOG descriptor that's already been trained for pedestrian detection using an SVM. You can create a cv2.hog descriptor object and then use the cv2.hog descriptor getDefaultPeopleDetector function to load the pre-trained SVM coefficients into it. Then you just call the detect multiscale method, similar to hair cascades on your image, and it returns the detected pedestrian bounding boxes. It makes it surprisingly easy to start detecting people right away.
But what if you want to detect something else, like cars or cats? You need to train your own detector.
Right. For creating your own custom object detectors for arbitrary objects, the book introduces the bag of words, or BOW, model adapted for visual features. This is also sometimes called bag of visual words, BOVW.
Bag of words, like for text analysis, how does that apply to images?
It's analogous. Instead of actual words, you use visual words. The process generally involves 1. Gathering training images. Lots of images containing your object, positive samples, and lots of images not containing it, negative samples. 2. Extracting local features. Run a feature detector and descriptor extractor like SIFT, SRF, or ORB on all your training images to get a large collection of local descriptors. 3. Building a visual vocabulary. Use a clustering algorithm, typically k-means clustering, on all these descriptors. The center of each cluster becomes a visual word in your vocabulary. 4. Representing images as histograms. For each training image, assign each of its local descriptors to the nearest visual word, cluster center. Then, create a histogram that counts how many times each visual word appears in that image. This histogram is the BOW representation of the image. 5. Training a classifier. Finally, train a classifier, like an SVM, on these BOW histograms using the positive and negative image labels. The SVM learns to distinguish the typical histogram patterns of object images from non-object images.
Wow, that's quite a process.
It is, but it's a powerful framework for learning object categories based on local features.
Now, how do you actually find the object in a new, larger image using this trained classifier?
To find objects that might be different sizes or in different parts of a new image, the book describes the classic techniques of sliding windows and image pyramids.
Sliding window.
Yeah, you take a window of a specific size, usually the size you train your classifier on, extract its features, compute its BOW histogram, and classify it using your SVM. Then you slide this window across the entire image, typically pixel by pixel or with some step size, repeating the classification at each location.
And image pyramids.
Because objects can appear at different scales, just using one window size isn't enough. So you create an image pyramid set of copies of the original image, each one progressively scaled down, or sometimes up. You then run the sliding window detector on each level of the pyramid. This allows you to detect the object regardless of its size in the original image.
That sounds computationally intensive.
It definitely can be, especially with dense sliding windows and mini pyramid levels. But it's a standard approach. The book walks through an example of training a BOW SVM to detect cars using this whole pipeline, including applying NMS at the end to clean up the detections.
And crucially, it shows you how to save your trained SVM models.
Yes, using methods like svm.save. This is really important. So you can train your detector once, which might take a while, and then just load the trained model, svm.load, whenever you want to use it for detection without having to go through the whole training process again.
Okay, makes sense. Now, once you can detect objects, the next logical step is often to track them as they move in a video. Chapter N of the book dives into the world of object tracking.
Right, following objects from frame to frame.
One fundamental way to find things that move is by looking at what's different from the background, right? Background subtraction.
Exactly. The idea is to build a model of the static background in a scene over time, and then identify pixels in the current frame that are significantly different from the background model. These differing pixels likely belong to moving foreground objects.
What kind of models does the book talk about?
It discusses a basic approach, which might involve simple frame differencing or maintaining an average background image, often combined with blurring and morphological operations, like eroding and dilating, to clean up the resulting foreground mask. But it also covers more sophisticated algorithms built into OpenCV.
Like MOG2 and KNN?
Yes. CV2.create background subtractor MOG2 implements an improved Gaussian mixture-based background-foreground segmentation algorithm. It models each background pixel's color as a mixture of Gaussian distributions, which helps it adapt to gradual lighting changes and things like waving trees. CV2.create background subtractor KNN uses a k-nearest neighbors approach, comparing pixel values to recent history to decide if they belong to the background. The book even briefly mentions other methods like GMG.
What's the main challenge with background subtraction?
The core challenge is dealing with dynamic backgrounds, like moving foliage, gradual or sudden illumination changes, shadows cast by moving objects, which might be falsely detected as foreground, and initializing the background model correctly. Each algorithm has different strengths and weaknesses in handling these issues.
Okay, so that finds moving regions. What if you want to track a specific object based on its appearance, like its color?
Another common approach is tracking based on color histograms. The book explains how you can first select the object you want to track, maybe by drawing a box around it in the first frame. You then calculate a color histogram, a representation of the distribution of colors, like hue and HSV color space, which is often good for this, just within that object region.
So you get a fingerprint of the object's colors.
Exactly. Then, for subsequent frames, you use something called histogram back projection, cv2.calcback project. This takes the object's histogram and creates a probability map across the new frame, where each pixel's value indicates how likely it is to belong to the object, based on its color matching the histogram.
And then you find the object in that probability map.
Right. Tracking algorithms like mean shift, cv2.mean shift, and cam shift, cv2.cam shift's continuously adaptive mean shift, can then efficiently find the peak, the mode in this probability map, in the vicinity of the object's last known position. Camshift is particularly nice because it also adapts the size of the search window as the object's apparent size changes.
What about predicting where the object is going?
To help smooth out the tracking, handle brief occlusions, and even predict where an object might be going next, the book introduces the Kalman filter, cv2.Kalman filter.
Kalman filters sound complex.
They are mathematically sophisticated, but the core idea is that they maintain an estimate of the object's current state, like position and velocity, and use a motion model to predict its state in the next frame. When a new measurement, like the position from camshift, becomes available, the Kalman filter optimally combines the prediction and the measurement, weighting them based on their uncertainties to produce an updated, more accurate state estimate. It's great for tracking objects with relatively predictable motion.
Interesting. The book also touches on programming paradigms here.
Yeah, interestingly, in the context of tracking, the book briefly discusses the difference between object-oriented programming, OOP, and functional programming styles, especially concerning how OpenCV is structured. It points out that many OpenCV components, like the Kalman filter or background subtractors, are implemented as objects that maintain their own internal state between calls.
Which can lead to side effects.
It can. If you modify the state of an object, it affects subsequent calls. This is typical of OOP, but it's something to be aware of, as opposed to a purely functional approach where functions always produce the same output for the same input without changing any state.
Good point. And this chapter culminates in a pedestrian tracker example.
Yes, finally, this chapter brings several techniques together in an example of a pedestrian tracker. It cleverly combines KNN background subtraction to initially detect moving regions that might be people, then uses mean shift, or perhaps cam shift, to track the color histogram of those regions, and incorporates a Kalman filter to predict their movement and make the tracking smoother and more robust to noise or brief disappearances. It's a nice demonstration of combining multiple methods. As we move into even more advanced territory, Chapter 9 of the book explores camera models and augmented reality, AR. This is where you start to really connect the 2D images your camera captures with the 3D world around it.
Right, bridging the gap between 2D and 3D. What do we need to know about the camera itself?
This chapter begins by explaining the fundamental parameters that define a camera model. There are intrinsic parameters, which describe the camera's internal geometry and optics. These include the focal length, often represented as x and alpha in pixel units, and the principal point, CSE, NDSE, which is the point where the optical axis intersects the image sensor. These are often combined into a 3x3 camera matrix, often called K.
And extrinsic parameters.
Then there are intrinsic parameters, which
Sure.
describe the camera's position and orientation, rotation, translation, in 3D world space. These define where the camera is and where it's looking. The book also touches on the field of view, FOV, which describes how much of the world the camera can see, and it's related to the focal length and sensor size.
Cameras aren't perfect, though, right? They distort the image.
Exactly. Real-world camera lenses aren't perfect, and they introduce geometric distortions into the images. The book discusses the most common types. Radial distortion, which causes straight lines near the edges of the image to appear curved, either outwards like a barrel distortion or inwards pincushion distortion, and tangential distortion, which occurs if the lens isn't perfectly parallel to the image sensor.
And we can correct for this.
Yes, these distortions can be mathematically modeled using a set of distortion coefficients, K1, K2, P1, P2, K3. Camera calibration is the process of finding both the intrinsic parameters, camera matrix, and these distortion coefficients for a specific camera. Once you have them, OpenCV provides functions to undistort images.
Okay, so knowing the camera's properties is key for AR. What are the steps involved in tracking something in 3D for AR?
With an understanding of how cameras work, and ideally, having calibrated your camera, the book outlines the general steps involved in 3D image tracking for visual augmented reality. It typically goes something like this. 1. Define or load your camera's intrinsic parameters and distortion coefficients. 2. Optionally, initialize a Kalman filter if you want smoother tracking of the object's pose. 3. Choose a reference image of the object you want to track. 4. Define or determine the 3D coordinates of some key points on the real-world object corresponding to features in the reference image. 5. Extract feature descriptors like ORB, SUFT, etc. from the 2D reference image at those key points. 6. Then, for each new incoming video frame, match these features against the reference image features. 6. Then, for each new incoming video frame, match these features against the reference image features. 6. Then, for each new incoming video frame, use the good 2D matches and their known corresponding 3D points to estimate the current 3D pose, rotation, and translation of the camera relative to the object. This crucial step is often done using CV2.solvepnp or CV2.solvepnp. 6. Then, for each new incoming video frame, optionally refine this pose estimate using the Kalman filter. 6. Then for each new incoming video frame, finally use the estimated pose to project your 3D virtual AR elements correctly onto the 2D image plane, making them appear attached to the real-world object.
Solve PNP. What does that stand for?
Perspective endpoint. It's the problem of finding the pose of a calibrated camera, given a set of n 3D points in the world, and their corresponding 2D projections in the image. CV2.solvepnp adds the RANSAC algorithm to make the pose estimation robust, even if some of the 2D 3D correspondences are incorrect, which can happen due to bad feature matches.
And the Kalman filter helps here how?
The Kalman filter in 3D tracking can help smooth out jittery pose estimates from SolvePNP from frame to frame. It uses a motion model, often assuming constant velocity or constant acceleration, to predict the object's pose, and then combines this prediction with the noisy measurement from SolvePNP to get a more stable result. The book briefly touches on the state vector, which might include position, orientation, velocities, and the transition matrix used in the filter.
Then you need to draw the AR stuff. Right. Once you have the estimated pose, rotation, and translation vectors, you can define your virtual object's points in the object's 3D coordinate system. Then you use CV2.projectPoints along with the camera matrix, distortion coefficients, and the estimated pose to calculate where those 3D points should appear in the 2D image. You can then draw lines, shapes, or overlay images at those projected 2D coordinates.
And the chapter wraps up with a demo.
Yeah, the chapter outlines an image tracking demo class that brings many of these concepts together, showing how to track a known reference image in a video feed and potentially overlay something onto it.
Very cool stuff. Finally, the last main chapter of the book, Chapter 10, gives us an introduction to the exciting world of neural networks with OpenCV. This feels like moving into the modern era of AI and vision.
Absolutely. While classical methods are still very important, neural networks, especially deep learning, have revolutionized many areas of computer vision in the last decade or so.
So the book starts with the basics, ANNs.
Yes, it starts with the fundamentals of artificial neural networks, or ANNs. It explains the biological inspiration, neurons, and the basic components of a simple feed-forward network. Artificial neurons, nodes or units, that receive inputs, compute a weighted sum, apply an activation function, and produce an output. Layers of these neurons. An input layer, receiving the raw data, one or more hidden layers where the computation happens, and an output layer, producing the final result. Layers of these neurons.
Connections between neurons, each having an associated weight that gets learned during training. Layers of these neurons. Activation functions like sigmoid, ROU, TON that introduce nonlinearity, allowing the network to learn complex patterns. The process of training, feeding the network labeled examples, calculating the error between the network's output and the true label forward pass, and using an algorithm like backpropagation to adjust the weights to reduce this error, backward pass. The process of training. And finally, testing the trained network on new unseen data to evaluate its performance, the process of training. It emphasizes that these are essentially powerful statistical models that learn complex mappings from input to output directly from data.
When you're designing one, how do you choose the layer sizes?
That's a key design choice. The input layer size is determined by the number of features you're feeding into the network to describe your input data, e.g., the number of pixels in a flattened image, or the size of a feature vector. The output layer size typically corresponds to the number of different categories or classes you want your network to be able to recognize or predict. If it's a regression problem, predicting a continuous value, the output layer might just have one neuron.
And the hidden layers.
The number and size of hidden layers are hyperparameters you often need to experiment with. More layers and neurons allow the network to learn more complex functions, but also increase the risk of overfitting, learning the training data too well and not generalizing to new data, and require more data and computation to train.
How do you actually build one in OpenCV?
The book then walks you through how to create and train a simple ANN in OpenCV using the cv2.mlan and MLP class, which implements a basic multi-layer perceptron, MLP. You create an instance using cv2.mlan and MLP create, define the structure, number of neurons in each layer, including input and output, using set layer sizes, maybe set the activation function and training parameters. Then you prepare your training data, input features and corresponding output labels, usually as NumPy arrays, and wrap them using cv2.mla train data create. Finally, you call the train method to teach the network.
It shows some examples.
Yeah, it provides basic example, perhaps classifying simple patterns, and then a slightly more involved one, like an animal classification task, using generated data, possibly with a hidden layer and training over multiple epochs. Pass it through the training data. It also tackles the classic Emmons handwritten digit classification problem.
Ah, MNList. The hello world of image classification.
Pretty much. It shows how you can take those 28 by 28 grayscale images of handwritten digits 0 through 9, flatten them into feature vectors, and train an ANN, MLP, to classify them. It demonstrates achieving reasonably high accuracy, showing the power of even simple neural networks on this task.
And then you can use that trained digit classifier.
Right. The book explains the typical pipeline for applying a trained classifier to new images. For the digit example, this would involve 1. Loading the saved, trained ANN model, n.load. 2. Loading a new image containing handwritten digits. 3. Pre-processing the image, maybe converting to grayscale, applying thresholding to get black digits on a white background, or vice versa, finding contours to isolate individual digits, and calculating bounding boxes. 4. Extracting each digit, cropping the image using the bounding box, resizing it to the size the network expects, example, 28 by 28 for MBIST, and maybe doing other normalization. 4. Extracting each digit. 5. Flattening the digit image into a feature vector. 4. Extracting each digit. 6. Feeding this vector to the predict method of the loaded ANN. 4. Extracting each digit. 7. Interpreting the output, which might be a vector of probabilities for each class, to get a predicted digit.
Okay, that makes sense. And you can save these ANNs too.
Yes, just like with SVMs, you can save your trained ANNs using an.save and load them later using an.load or cv2.mlstat model more generally.
What else can you do with these ANNs?
The book briefly mentions other potential applications, like extending classification to video frames, or potentially using them for more complex optical character recognition, OCR tasks, beyond just digits.
But then it moves on to the really deep stuff, DNNs.
Exactly. The chapter then introduces deep neural networks, or DNNs, which are essentially ANNs with many more hidden layers, hence deep. It highlights that while you can build DNNs layer by layer in some frameworks, a very common practice in OpenCV is to leverage pre-trained models.
Pre-trained meaning someone else already did the hard work of training them on massive data sets.
Precisely. Models trained on huge data sets like ImageNet have learned very powerful feature representations. These models are often developed and trained using dedicated deep learning frameworks like TensorFlow, PyTorch, Torch, Caffe, Darknet, used by YOLO, or serialized in standard formats like OmenNX, Open Neural Network Exchange. Intel also has its OpenVINO toolkit with a model zoo.
And OpenCV can load models from all these different places.
Amazingly, yes. OpenCV's DNN module provides functions like cv2.dnn.readnet from CAFES, cv2.dnn.readnet from Torch, cv2.dnn.readnet from Darknet, cv2.dnn.readnet from Darknet, cv2.dnn.readnet from Model Optimizer for OpenBio, to load network architectures and pre-trained weights from files saved by these frameworks.
That's incredibly useful. Avoids framework lock-in.
It really is. Once you load a network, you often need to pre-process your input image into a specific format called a blob before feeding it to the network. The cv2.dnn.blob from image function is designed for this. It handles things like resizing the image to the network's expected input size, optionally swapping color channels like BGR to RGB, performing mean subtraction and scaling values, then arranges the data in the required batch format.
What kind of tasks can you do with these pre-trained DNNs?
The book gives a couple of examples. One uses a popular object detection model called MobileNet SSD, single-shot multi-box detector. You load the pre-trained model, prepare an input blob, pass it through the network using net.forward, and the output gives you bounding boxes, class labels like person, car, dog, and confidence scores for detected objects in the image. MobileNets are designed to be efficient for running on devices with limited resources.
And face analysis.
It then delves into a multi-stage face analysis example. First, it uses a pre-trained DNN, likely CAFE-based in the example, specifically for highly accurate face detection. Then, for each detected face, it extracts the face region of interest, ROI, pre-processes it, the example mentions making it square, and feeds it separately into other pre-trained DNNs, one trained for age estimation and another trained for gender classification. The results are then displayed alongside the detected face.
So using specialized networks for different subtasks.
Exactly.
Yeah.
It shows how you can chain these powerful pre-trained models together to build sophisticated applications without having to train them yourself from scratch.
And finally, there's an appendix about color curves.
Yeah, just a brief Appendix A that touches on a more creative application, bending color space using curves. It explains the concept of applying nonlinear adjustments, curves, independently to the blue, green, and red channels of an image. By carefully designing these curves, you can emulate the distinct color palettes and contrast characteristics of different types of classic photographic film, like the warm tones of Kodak Portra, the vibrant look of Fuji Provia, or even achieve artistic effects like cross-processing. It's a nod to the artistic possibilities within image processing.
Wow, that was a whirlwind tour through the incredible landscape of computer vision. As you can see, learning OpenCV for computer vision with Python 3 really lives up to its name, covering everything from the foundational steps of setting up the library to the cutting edge of deep learning.
It really does cover a lot of ground. And while we've, hit the highlights today, remember that this is just a taste of the vast capabilities that OpenCV offers. Hopefully, this deep dive has given everyone a solid understanding of the core concepts and maybe sparked some curiosity to explore specific areas further.
Yeah, definitely. So as you reflect on all the techniques we've discussed, from basic image tweaks like blurring and filtering to finding contours, recognizing faces, matching features, tracking objects, and even using these complex neural networks, consider this. What problem in your own life or field could be tackled? Or what new creation could be brought to life by applying these computer vision methods?
That's a great question to ponder. The possibilities are really endless.
We encourage you to pick up Learning OpenCV 4 if you want the full details, or explore the wealth of online resources and tutorials to continue your journey into this fascinating domain.
Thanks for diving deep with us.